if I change my objective function to minimize minus x1, so consider minimize minus x1 subject to the same constraints. Then by looking at the picture, we can see that all blue points would be optimal with the optimal value of minus 4. Okay, so we have many optimal solutions each with same value of minus 4. In fact, with a little bit of thought, note, given an LP in any of the three forms, if x1 is in the feasible region and if x2 is also in the feasible region, then the line joining x1 and x2 also lies within the feasible set R. Okay, so that means you take any point between x1 and x2 and that would also lie in the feasible region. And again, in this picture, which is getting messier now, you take any 2 points, for example here and here, and draw these, connect these 2 points and take any point on that line segment, it will lie inside the feasible region. And that is very easy to show by means of these inequalities. You can try it yourself. For example, the midpoint will lie in the set R again, and so will other points. Okay, so that means R is a convex set and the objective function is a convex function, which means that every local solution is also a global optimal solution. Okay, so this is a result which we will try to revisit in the next chapter again. For now, we will just assume that this result is known to us. Later on, we will do this result for general convex functions and then revisit this linear programming case again. But you should remember that if a linear program has a local solution, then it must be the global solution of that linear program. Okay, so So this linearity actually leads us to some very nice properties. So let me draw a feasible region again. If I look at any point x1, so let x1 be any point in R, we say, so this is some terminology, a direction D in Rn is a feasible direction if I can take a small step in that direction and still be feasible. For some scalar that means at x1, if I have a direction D like this, it's a feasible direction. In fact, at x1 I have many feasible directions in which I can go. Since x1 is in the interior of the feasible region, I can pretty much go in any direction, and that would be a feasible direction. On the other hand, if I am at a point x2, then the direction 1, 0 is not, so transpose is not a feasible direction, because the moment I take even the tiniest of steps in this direction from x2, I will leave the feasible region. Okay, so a feasible direction really depends on where my point is. Okay, 1, 0 is a feasible direction here. At point x1, but it is not a feasible direction at point x2. We already know what descent directions are. So so in this particular case, suppose I am minimizing the objective function that we had originally, then the direction if I walk along the x1 axis, then it's a descent direction. Because from the definition that we have seen in case of unconstrained optimization in the previous lectures, D transpose grad f which is strictly less than 0. So that means if I try to go in this direction, my objective function will decrease, and that is easy to see. So as long as I have a descent direction, and as long as I have a feasible direction along which I can move, and it is also a descent direction, then surely I can get a better point than my existing point. Okay, so so at x1 I have many descent directions, and I can take any one, and I can keep going, and we can easily see that in LP these descent directions are the same everywhere. Same at every feasible point. So so you pick, so for example 1, 0 is a descent direction at x1, but it is also a descent direction at x2, even though it may not be feasible, but at least the objective will go down if I try to move towards the right. And that happens because my gradient is constant. It's independent of where I am currently. So that means if I find a descent direction at any point, then I can keep going in that direction and my function will continue to decrease and decrease and decrease until I hit some boundary. And then I can try to find another descent direction and try to keep moving in that direction until I hit the next boundary, and so on and so forth. So intuitively what we can say is that if a linear program has an optimal value, then one of the boundary points should also have that optimal value. Okay. So in particular, if an LP has a solution as an optimal solution, one of the corner points must be optimal. It's not even clear that every linear program must have a corner point. So for example, look at the feasible region bounded by two parallel lines, let's say between 1 and 0. So the feasible region is the region between so everything in this green area is feasible and there are no corner points, but if there is a finite optimal solution, then I must hit some boundary point which prevents me in going any further. Okay. So because otherwise I would be able to keep going in that direction forever and I may become unbounded. Okay, so that brings us to the idea of unbounded LPs. So again, if I look at the problem I wrote earlier with the feasible region roughly of this form, so if I drop some of the constraints, so we dropped my feasible region R is now unbounded, and my current point is still optimal for objective function minus 4x1 plus x2. But if I try to change my objective function, it might become unbounded. So for example, if f is set to minus x2, and if I'm trying to minimize f over the given region, this will give me an unbounded solution. Okay, or we say that the problem is unbounded. So notice that if optimal value is unbounded, then R is also unbounded. However, the converse is not true in general. You can show, we just showed an example of R being unbounded, but some corner point still being optimal. The last thing that we would like to discuss is the idea of this vertex. This is also a corner point. So what you can actually show with little bit of analysis and thought is that for a point, let's say x1, to be a vertex, of R, n linearly independent constraints must be active there. So for example, look at any vertex or corner point and you will see that at least in this 2D case it is found by intersection of two constraints. So in the next part we will talk about how to find some good corner points which might be the solutions of the linear program, and then go to somewhat more important topics and more detailed topics. So with that I will stop and continue in the next part of this lecture later. Thank you and bye-bye.